When we talk about changes that can occur to matter, changes are like alterations. And so we have physical changes and we have chemical changes. Physical changes are ones where the alterations that occur might result in a difference in properties of the substance that we're looking at, the material that we're looking at, but it's not going to change the fundamental composition of what makes that material up. So for instance, if you have a piece of metal and you hammer on it and flatten it out, you're not changing the chemical formula of what that material is, but you might be changing, the length, the width, or the thickness of that piece of metal. Same thing with phase changes. If I take an ice cube, solid H2O, and I heat it up or warm it up, it will turn into liquid H2O. If I lower the temperature, that liquid H2O will turn back into solid H2O or ice. May not look exactly the same as the original form that it had, but looking at the composition of the material, it's still H2O. It's just a difference in the arrangement of the particles, but not what makes them up. Physical changes are going to involve changes to the intermolecular force attractions that are occurring. And so how we can tell whether a change is going to be a physical change or a chemical change oftentimes can boil down to, no pun intended, the question, is it reversible? If it is easily reversible, then more than likely it is a physical change. So again, you take an ice cube, you melt it, you lower the temperature, you can refreeze that liquid water into solid H2O. If we look at the substance that is involved in the change and we measure its mass, if the mass of that material is the same as it was before the change occurred, that means nothing was added to it or removed from it. And so therefore, we can assume that it is a physical change. Nothing brand new is formed. In a chemical change, the alterations that we see to the material will result in one or more new substances being formed through a chemical reaction. And these new substances will have different characteristics and properties, and most importantly, they will have a new chemical composition to them, a new makeup. Now, practically speaking, how can we, by observing a change in matter, determine that it's a chemical change? Well, one of the easiest ways is it produces some sort of energy change, and energy can be in the form of heat or light. It will either be absorbed, like in photosynthesis, it absorbs light energy, or it might be emitted. We talk about wood in a campfire that's burning. You have the emission of light, you have the emission of heat. Another sign of a chemical change is the formation of an insoluble precipitate. When we mix solutions together, and then all of a sudden there's this solid that appears, or a cloudiness that appears in the solution. That is the formation of some ionic substance that is insoluble and it can't stay dissolved. So it precipitates out and oftentimes will settle to the bottom of the reaction vessel. Then we have the formation of a gas. Now the caveat here is that it's not the formation of gas due to boiling. You put water on the stove to make spaghetti, you turn on the heat, and eventually you're going to get bubbles forming. But that's a phase change. So that's a physical change. This would be like if you have baking soda and vinegar used to make a volcano for a science project. When you mix the two of those together, it effervesces, it bubbles. That generation of a gas indicates a chemical change is taking place. And finally, if we see a color change, and again, there's a caveat here, the color change isn't one that's simply the mixing of colors. You're not mixing a yellow and a blue solution together to create a green solution. This would be like two colorless solutions mixed together, and all of a sudden you see bright hot pink out of nowhere. Now, these new substances are being formed because what you have is the breaking of some initial bonds in the reactants, and then those atoms are now reforming and forming new bonds to create the new substance. So very similar to you build a Lego model that is on the front of the box, and then you tear the bricks apart, you break that model down, and you build something new, but you use all the Lego bricks. That would be analogous to a chemical change taking place. So again, how can we tell? What's the practical ways to tell? You ask yourself, is it reversible? Typically, chemical changes are not going to be easily reversible. When we look at the material in question and ask ourselves, is this undergoing a chemical change? We can use the law of conservation to help us here again. If the mass after the change has occurred to that material is different than the mass before the change occurred, then you know it either picked up some new material or it lost something. And so there is your evidence that bonds were either formed or broken in that chemical change process. Now, it's nice to have things that we think are pretty cut and dry, but oftentimes in reality, things are a little more complex than we might think. And so oftentimes we think of the process of dissolving as one that we might classify as a physical change. But some arguments can be made for it being a chemical change. And so what I invite you to do is take a moment and see if you can make an argument for dissolving being a chemical change or dissolving being a physical change. All right, so if we look at the arguments for it being a physical change, one, dissolving, we can evaporate the solvent off and recover the solute that we dissolved. So it is reversible rather easily. Plus, the amount that we dissolved, if we compare that to the amount that we recover, should be the same. So both of those would be arguments for dissolving being a physical change. If we consider, though, what's happening on the particulate level with dissolving, though, we have bonds that are being broken. The ionic attractions between the sodium and the chloride ions in the model that we see here are indeed being broken. And you have new attractions occurring, new interactions occurring between the polar water molecules and the ionic charges. So you have ion dipole forces, which are being created here as well, or which were not present in the first place. So depending on your perspective, you can argue and make a case for processes like dissolving being physical in nature or chemical in nature. Remember that chemistry really has a language all of its own, and one in which our alphabet are the element symbols of the periodic table. If we take those letters, if you will, and we put them together in a meaningful way, we can create chemical formulas which represent actual substances, much the way we can sequence our ABCs into ways that actually form real words. We can then take those words and put them together in a certain way to create a sentence which expresses an idea about something. Well, in chemistry, we have chemical reactions, chemical equations that string together these formulas in such a way that describes a chemical change that's taking place. And so when we look at a chemical equation, there are some key parts that are the same for all types of chemical equations. The most notable and kind of the focal point is usually the reaction arrow. And when that's read aloud, that's read as yields. In a math equation, you have the two parallel lines. That's an equal sign, and we say it equals. In a chemical equation, the arrow is represented or read as yields. The reactants are typically going to be found to the left side of the reaction arrow or on the tail end of the arrow, whereas the products are going to be found at the head of the arrow. Usually it's on the right side of the equation, but again, it's the head of the arrow. Numbers that are found in front of the chemical formulas represent multipliers, and we call them coefficients. They tell us how many of that particular substance we typically have. And then oftentimes there will be subscripted letters in parentheses. This gives us a clue as to what state of matter each of those materials is in. Now, when we look at different types of chemical equations, different ways that we can represent these changes that are occurring, we have some options. Word equations would probably be the simplest in terms of composing them. It's based on the names of the compounds. We don't have to get into the intricacies of the chemical formulas, but it does take on that equation type format. Formula equations are going to have that equation format with that yields arrow in there, but now instead of the names, we use chemical formulas. Now, depending on how much detail we're showing, if we're just showing the reactants that are involved and the products that are formed, but we're not really, abiding by the law of conservation of matter, then that's what's called a skeleton equation. It's a bare bones equation, just tells us what are we starting with, what are we ending with. In order for that to accurately represent the chemical changes that would take place, we need to make sure that we have the same amount of atoms to start as we do to finish. And so we have a balanced equation which uses coefficients in front of the formulas to make sure that we have that that balance, right? The same number of atoms of each type on the left side and the right side of the equation. Now, when it comes to mixing things together, sometimes those particles, remember he said it's like breaking down into Lego bricks, sometimes those bricks are going to be used in the new model, and other times we might say, well, they're here, I haven't lost them, but I'm just not using them in this new material that I'm creating here. And so they're just kind of sitting there and watching. And we would call those spectator ions. And so an ionic equation is the first step in determining what are those spectators. An ionic equation is one that tells us in solution, what is this material actually going to exist as? Is it going to be a whole material, or is it going to be in dissociated form where it's in its individual ions? And so the net ionic equation then takes into account, okay, which of those ions that dissociated, which ones are actually involved in making something new, and which ones are just kind of hanging out and being spectators. So when it comes to translating changes that are occurring, context clues, context clues, context clues. Got to read carefully and think about what is being described to you. You want to write the correct chemical formula based on which type of compound it is, whether it's ionic, molecular, or acid. Don't forget about the 7 diatomic elements. Remember, there are 7. You start with element 7, nitrogen, and literally form a 7 on the periodic table. That's 6 of them. The 7th one would be hydrogen. So when it comes to interpreting or translating an equation from one form to another, we need to, again, read carefully. So if we look at our example here, sodium metal reacts with water to produce sodium hydroxide solution and hydrogen gas. And so the first thing we need to do is to determine what are we starting with, what are we ending with. And we use the context clues to help us. So the first thing we read is sodium metal reacts with water to produce sodium hydroxide solution and hydrogen gas. The phrasing is key here. So we know we're starting with sodium metal and water, and again, the context clue is to produce, meaning something wasn't there to start with, we're now making it. And what we're making are going to be our products, so that would be the sodium hydroxide solution and the hydrogen gas. So now taking that information and translating it from a sentence form into an equation form, we would have sodium, it's a metal, right? The only metal that we have that's not a solid would be mercury under normal conditions, room conditions. So that's why we have the subscript S there, plus water, all right? And water, again, under normal conditions is going to be a liquid, so we can assume that L is the state there. Sodium hydroxide solution, anything that's in solution, we're going to assume it's a water-based solution. We know there's water present, so that would be sodium hydroxide aqueous plus hydrogen gas. So subscript G. Translating that into a skeleton equation, we now take those names and write their appropriate formulas. So we have sodium, all right, and sodium is a monatomic element, it's not diatomic, so it's got to be sodium subscript S. You have water, H2O liquid, yielding sodium hydroxide, so we can use the charges to help make sure we have the right formula there, NaOH, aqueous, and then finally hydrogen gas. Hydrogen is a diatomic, so it is by itself, so it automatically gets the 2 written after that formula. If we take a look at this example, mercury 2 oxide is synthesized from elemental mercury and oxygen. Now again, reading carefully, the first thing listed, mercury 2 oxide, if you read carefully, it's not there to start. It's synthesized from elemental mercury and oxygen. So mercury 2 oxide is a product. What it's being produced from is elemental mercury and oxygen. So those are our reactants. So when we write this in word equation format, mercury, again mentioned previously, that is a liquid under room conditions. Oxygen is a gas. And mercury 2 oxide, there's no indication of what it is, but most ionic substances are going to have high melting points, so it's a pretty safe bet to assume that it's going to be a solid. Translating that into an equation form, a skeleton equation, right? Mercury is an element all by itself, but it's not diatomic, so it would simply be Hg in the liquid state, plus oxygen all by itself, and oxygen is one of the diatomics, so we have O2 gas. On the product side, mercury 2 oxide, again, that Roman numeral is a dead giveaway that it's an ionic substance, so we use the charges to make sure that we have the correct ratio of those ions, and so the formula for mercury 2 oxide would be HgO, and again, in the solid state. Some reminders when it comes to going from a skeleton equation to making sure that an equation is balanced. We need to make sure in the end that we have the same number of each type of atom on both sides of the equation. So the first thing to do would be to take an inventory. Now you can physically write this inventory down if you like, or you can just keep track of it in your head and do one element at a time. And so you take that inventory, determine what needs balancing, what doesn't need balancing. And then you pick an element to start balancing first. Now, there's not necessarily a rhyme or reason to which one to pick first, because in the end they're all going to be balanced. But there might be some advantages to leaving some until the end. So if an element is all by itself, like your diatomics, like oxygen or nitrogen, or if it's an element that is found all throughout in lots of different reactants and products, leave that for the end, because they can be a little tricky to try and balance right from the get-go. So once you've picked an element, then you're going to add coefficients in front of the formulas in such a way that when you count up how many of each atom you've got on each side, you come to a balance. Can't change subscripts, only change coefficients. And then as you make those changes, if you're writing your inventory down, cross out the number that you have and put the new total. Or if you're doing it in your head, just update what that total count now is. Some other tips for balancing equations. If you notice that there's a polyatomic ion present, do a quick look on the other side and see, do you have the same polyatomic ion? And is there any other source of those potential elements that are participating in that polyatomic ion? If the only place you have them is as a part of those polyatomic ions, then just balance that as a single unit. Can help to streamline things a little bit. Sometimes if you have water involved in the equation, instead of writing it as H2O, rewrite it as HOH, hydrogen hydroxide. Nothing wrong with doing it that way. It's accurate. Plus, the benefit there would be that it gives you a source of hydroxide ion, so that if you have a hydroxide on the other side, you can balance as polyatomic ions. All right, and then finally, you might get to a point where you're just going back and forth and you're like, I just can't get this to balance. If the problem you have is that you have an odd number of one element on one side and an even number on the other, sometimes when you're balancing, you get going back and forth and you're just like, I'm spinning my wheels here. I can't get these to balance. And that's because one side has an odd number, the other side has an even number. If that's the case, the thing to do is go back for the coefficients, for the elements that you did get balanced, double them across the board. And what that will do, by doubling, anything times 2 is an even number. And so that will eliminate the odd number problem, and you should be able to balance that last element a lot more easily. So in your notes, there are several skeleton equations, some of them word equations, asking you to translate them into skeleton equations. So take some time, try those on your own, and then come back here and restart the video, and then the solutions will be presented to you. So hopefully you can compare what you see here to the equations that you have in your notes, and hopefully they match up. Now, if there's one type of question that is, I would say, especially kind of a favorite on the AP exam, it's particulate diagrams. And that's because it's one thing to talk about a change, it's another thing to describe it in written form, but to actually physically think about what are the particles doing, what is this going to look like if we could peer down that far. So it's important that we're able to describe changes in such a way as well, whether they're chemical changes or physical changes. So things to pay attention to: the materials that are involved. Are they diatomics? If so, they should be drawn as diatomic particles. Secondly, the ratio of the particles that are involved. So you got to pay attention to stoichiometry. And finally, you also have to pay attention to the concept of limiting and excess reactants and make sure that your diagrams are reflecting those. So if we take a look at this reaction here, or we look at this diagram, we see hydrogen and nitrogen, both gases. So we see that they are accurately represented in their diatomic natures. We see that the particles are also randomly dispersed, and they are spread apart from one another, which is indicative of what a gas would look like. If we look at the reaction between nitrogen and hydrogen, they can combine to form ammonia, NH3. So in our resulting diagram, we should see a new type of particle, one that has one nitrogen atom and 3 hydrogen atoms, and we see that. But notice that in the balanced equation, that for every 1 nitrogen that's consumed, 3 hydrogens are consumed. So in looking at what we have to start with, we had 3 hydrogen molecules, 3 nitrogen molecules. Well, that 1:3 ratio means that only one of the nitrogens, the N2s, are going to be used up, and all 3 of those H2 molecules will be consumed. And so we're going to get 2 of the ammonia molecules that are able to be generated from that 1 nitrogen and 3 hydrogens. And that leaves us with 2 intact nitrogen molecules left over, which is what we see in our diagram. If we take a look at this example, which of the following particulate diagrams best shows the formation of water vapor from hydrogen gas and oxygen gas in a rigid container at 125 degrees Celsius? So again, we're talking about hydrogen gas, oxygen gas. What do we know about hydrogen and oxygen? They're diatomics. So if they are diatomics, they ought to be illustrated that way, and choices A and B don't do that. So if we consider the difference between C and D, we see diatomic molecules to start. We see water molecules on the product side. But now it comes down to stoichiometry. And when we think about the stoichiometry of water, it's 2 parts hydrogen to 1 part oxygen. So that means that we need twice as many hydrogen atoms, molecules, as we have oxygen molecules in that 2-to-1 ratio. And notice that there are no leftovers, no excess reactants. So that means that whatever we've got has to match that 2-to-1 ratio completely. And we see that in option C.